Well, it's a pleasure to be here to talk to you a little bit about some views on outflows and their role in star formation. But then, I saw that you did all this cool work with all these different hydrocodes, and you learned about adaptive mesh refinement and about Riemann solvers and magnetic fields. And then, of course, I couldn't help myself, so I also want to do a little bit of an ENSO tutorial, sort of the code I've been involved with since the late 90s, or 1998 or so. And now that you have all these skills of already using others, I thought, what better opportunity than use the chance to also get your hands dirty with ENSO. And so for the outline, what I want to do, actually, let me just sort of say some of the work I'll talk about is related to magnetic fields in galaxies, a simple numerical experiment I did with a former graduate student of mine, Peng Wang, who by now actually works for NVIDIA. And then sort of the main part, perhaps, is about the simulation that I'm showing the movie here, where we followed the formation of a molecular cloud, the fragmentation, formation of stars, followed how their outflows interact with the magnetic field in the cloud, and through that drive turbulence on small scales and have quite a significant impact on star formation efficiency. And then I just want to make a few comments based on lessons learned from these two calculations of how this might relate to doing simulations where you aim to form galaxies one star at a time. So where you really try to do this fully cosmological, make the very first galaxies in the universe, and just show you some indications of where I think we're headed and what's sort of possible nowadays with these types of codes that we have available. So, okay, I already sort of walked you through the outline. I think perhaps this is mostly just an information slide that you'll have available to sort of where to find information about this code, enso-project.org. We finally published a code paper on ENSO where you can see sort of many examples of some of the capabilities of the code. And you'll find that under that number on the archive. But what I'd like to ask you to do is actually go to this website now. This is sort of a simple tutorial I put together. I originally did this for a radiation transport conference, summer school in Leiden a couple of months ago. And what I give on that tutorial are instructions how to download ENSO. Actually, you already get the developer's version. Check it out of Bitbucket. Then I'll also give instructions of how to download a Viz tool that's a terrible, totally ugly hack that I wrote in IDL starting in the late 90s because we had no tools at all to look at AMR data. But I hear many of you will already learned about YT, which is an excellent tool to also analyze ENSO data. And so you could play with that. What you'll find on here is really step-by-step instructions, how to check out the code, how to modify the makefile to what you need to do, how to change options that are relevant for you to make the code run faster, turn off debugging and the like. And then walk you through how to run some simple test problems first. And so especially for this today, I added a little section of how to run the Burkert and Bodenheimer collapse test, where you can sort of follow the fragmentation of a highly idealized isothermal cloud. And I make some suggestion on the website of how to modify the file that already comes with the ENSO distribution. So you get 12 levels of refinement, and you see nicely how the fragments form, and it still runs in one process on your laptop in 5 minutes. So I encourage you, the ones of you that are interested, if you have your laptop out, just follow along the tutorial. It should be totally self-explanatory. And I'll go ahead and talk more about sort of the science topics I have in mind, but try not to be too long. So we'll have time afterwards for the ones that are interested in doing this and sort of working through it. I can help you with some of the questions you might have. So we'll do everything compressed. Yeah? Okay. So some of the fascination we had with the star formation a few years ago was to sort of try to make sense and sort of try to ask this very simple question of whether these outflows that we observe really in all molecular clouds around all these protostellar objects, whether they do or do not have a significant impact on the cloud as a whole, and whether they have anything to do with the regulation of star formation in the cloud. And some of the very nice examples, I'm sure you've seen these images already of NGC 1333 in Persis. When you look at the optical image, you see some evidence of outflows already in some of these objects, but just adding Spitzer data, it becomes just entirely obvious to the eye that at least it sort of shapes part of this cloud. Now, on perhaps larger scales, if you look at the Large Magellanic Cloud, you get this impression. Here we've got an optical image overlaid with very narrow band imaging. You see the emission lines. You see lots of evidence of star formation. Here's really the massive stars that you're picking out. What's beautiful, of course, since the Spitzer data again, you get all this appreciation of really where the gas lives. And perhaps even more impressive is with the current Herschel data, just fills up the cloud completely. So you have this reservoir of gas that can make stars, even in these small galaxies already inside our Milky Way. Now, I love doing astronomy by keynote. This is, anyhow. So I'm sure many lecturers already impressed upon you the importance of magnetic fields in the process of making molecular clouds themselves, assembling molecular clouds out of the cold atomic gas, and also the role it might play in really the dynamics of the molecular cloud formation and fragmentation. We also had a beautiful example today, the role of magnetic fields in determining whether you can make disks around protostars or not. And so this really becomes a sort of a rather fundamental topic, actually, if you think about this in a cosmological context, of where we're trying to understand also where does in fact this magnetic field come from. And so what I want to walk you through is there's of course lots of observational evidence. I'm sure you already heard a lot about. We can sort of measure magnetic field distribution, sort of rough values of the magnetic field strength in galaxies, but also molecular clouds. One particularly nice graph I like is from this older work by Rainer Beck that actually sort of nicely shows in this galaxy as a function of distance, sort of azimuthally averaged, the different contributions of all these different energy densities. And so you've got molecular gas, of course the thermal energy is very low. Going up, you have the ionized gas. Okay, the thermal pressure still doesn't contribute that much. The regular magnetic field here already dominates the thermal pressure of the ionized gas. Then you look at the turbulent component, you just get from line widths that you can measure. And then you look at the total magnetic field. And here is really the distinction between small scale field and sort of larger scale ordered field that sort of nicely is separated there. But in any case, I'm sad to report that essentially all simulations of galaxy formation we do today only include essentially the thermal pressure that is shown by the ionized gas. And we'd love to have the turbulent pressure in there, but to be honest, the resolutions at which galaxy formation simulations are carried out that don't even resolve the scale height of the disk of the galaxy, of course, have no hope in getting a sensible description of the turbulence inside the disk. If I have 400 parsec resolution and a scale height of 120 parsec, it would be not very nice to claim that I'm describing turbulence correctly. And so But however, much more relevant here directly from observations, though, is that magnetic field pressure, and here we didn't really separate out what cosmic ray pressure would, on top of it, provide, is really a crucial ingredient also on very large scales, and sort of this entire environment that you want to think about if you think about star formation, because that's what creates your initial conditions. It's really in the context of the galaxy that you form molecular clouds, you have molecular clouds form, or be born and die through it. So motivated through this, we said, okay, let's do some super simple numerical experiments. We took our adaptive mesh refinement code ENSO, implemented a way to solve the ideal MHD equations, and then just did the simplest conceivable experiment that we had, could think of, right? So we have a static potential, an NFW halo, so just a dark matter halo, in which so we have a ball of dark matter, 10 to the 10 solar masses. We wanted to take a small galaxy because it'll give us more resolution elements, finer resolution. So we went to a few parsec, to 10 parsec resolutions. So we had hoped to at least describe a little bit of the disk physics in this. And then we took in this static potential, we imagined gas distributed like the dark matter, having turbulent motions already, but also a coherent spin to it. Okay, so that setup will naturally allow the gas to contract, essentially mostly initially because of the dark matter potential, but then reach Keplerian rotation and sort of follow and sort of build a nice little disk galaxy. And then what we wanted to do is evolve it for quite some time to sort of study how that disk evolves. Super simple. No star formation, and feedback we model purely by having what's called this polytropic equation of state, that if the gas gets to high density, the pressure increases rapidly and it sort of stabilizes the collapse of small clumps. And that's what you then right away see sort of in the simulation results. If you look at the pressure here, for example, you get all these clumps, and people have termed this sort of gravothermal or turbulent disks, where it's really these clumps that sort of steer material there. Interestingly, what you have in gas-rich disks always, you're sort of unstable to have this large clumps form. You get sort of vorticity-driven instability. If we had a more star-rich system, sort of a more collisionless fluid, we'd at that point would get more spiral arm instabilities. But in any case, it was sort of a nice enough little object that afforded us to have many dynamical times in the system, and it sort of would drive magnetic fields in the correct geometry. And so what we then did is we added a super, super low magnetic field, a nanogauss strength, nowhere near the thermal pressure of the gas that we had to begin with. And we wanted to specify it only by one parameter, so we just specified the amplitude, and we used the uniform field. But one time we did it along the rotation axis, and one time we did it vertical to the rotation axis, and actually find no difference from that. Makes sense because it's so many dynamical timescales that you actually wind the field very rapidly. What you notice is that there is actually, in what the disk now looks like, there's not too much difference at all. Whether you have, with a magnetic field, it's slightly thicker than in the one without B field after this time. The interesting part, though, is we sort of plot this plasma beta, which I'm sure you learned about. It's exactly that parameter that's exactly the other way how you expect it to be. It's the ratio of the gas pressure to the magnetic pressure. So for very large beta, magnetic fields play no role whatsoever. And for very low beta, the magnetic fields start dominating actual the forces just from the simple pressure term. Now, what you see as a function of time, if we just selected the material in the disk, if you use the warm gas, it takes a while. We'll see that magnetic field gets more and more and more and more important as time goes on. So the parameter drops, and you're at equipartition when this reaches unity. However, for the cold disk gas, you already see that you're completely magnetically dominated. And the interesting part, actually, in this simulation, when I've just looked at the rough values of the field strength we get in the different phases of the disk, it already matches Milky Way values. And that's, in a way, not something we expected because it's just a tiny galaxy, 10 to the 10 solar masses. It is nowhere, you didn't play with that at all. It's really just sort of a simple effect that the thermal pressures that we have in this gas here are just like what we have in the Milky Way because of the type of cooling that we use. So we have a phase at 10 to the 4 Kelvin, when we have a cold phase in this case down to 300 Kelvin. And what happens is that all these vertical motions that you have in the gas continuously amplify the field. If the field gets too strong, its equation of state is more like 4/3, more like a relativistic fluid, but the surrounding material is isothermal. So you've got two fluids, one with a stiffer equation of state than the other, and the one that's stiffer will just lift itself off. And in fact, that's exactly what we see. You see magnetic fields bubbling out into the halo of this galaxy. So the reason that we observe equipartition in the magnetic field in the Milky Way is really not that the dynamo just managed to get it there. This very likely happened a long time ago, and the magnetic field since then is continuously amplified, but then just populates the halo. It just lifts out of the gas, and you can't support that much field. It just will lift out. And we can see that a little bit here, sort of in plots of the plasma beta, when we look at it edge on, and this is a funny color map, but the lowest values are these red regions, and you see exactly in these polar regions how magnetic field, in fact, sort of bubbles out of these galaxies. If I evolve this longer, or I start with a slightly larger field, so I don't have to evolve quite as long, I actually can see the magnetic field becoming completely dominant over the entire halo of the galaxy. In fact, I do believe that fields actually will have play a large role in understanding how gas is accreted onto galaxies. And there's an enormous amount of future work one could do on this, and I encourage you very much, using your fantastic tools that you learned, turn on the B field. Sure.
Is there any observational evidence or physical reason what would be the reasonable assumption for initial condition for the magnet?
There's a whole bunch, and there's an enormous literature on this. It's funny, it goes from AGN to supernovae to Biermann batteries and early ionization fronts to large-scale structure shocks and to sort of topological defects in the QCD phase transition, to the electroweak phase transition, to fields. Sorry, I could go on, but it's a couple of hundred. At the end, though, I think you really just want to think of this diagram. And what this sort of shows you is that even if I start with something absurdly small, it really doesn't matter. The timescale is super fast. So I will amplify any tiny field extraordinarily fast. And that's just this nature of the small-scale dynamo. I'm sure you already heard about is when you have a turbulent cascade, the way turbulence decays and makes it to the dissipation scale always has a component that's vertical. And all these vertical elements of the fluid flow, at the time when the field is not strong, all it'll do is wind up field. And it'll wind it up until finally the field acts back. Right? And so there is always a scale you want to think of that's between the dissipative scale, sort of the viscous scale, and the sort of driving scale or natural scale of your problem you're interested in. There's always a scale in between at which the magnetic field is in equipartition. And this is the relevant scale if you think about viscous transport, thermal conduction, all these processes. So don't think about particle-particle collisions. That works great in a textbook, but in reality it's very unlikely to be relevant in these applications where you have a real plasma. Sorry, that's a long answer. But anyhow, and so that was what I already said in words. If I just sort of look at how the B field and density are correlated in these simulations, you just naturally get out the typical values you observe. And Dubois and Tessier also did a very similar work just a year later. And I think this is really a fantastic area to actually explore a lot more how this cosmic dynamo works over time, what the impacts are in different types of galaxies, how it works with small ones versus big ones. There's many observational probes correlating magnesium-2 absorbers, for example, with with the polarization direction of the background quasars that you observe them in, etc. Anyhow, but this was just to motivate to say we got great tools. It's a fantastic field. Just go for it. Like there's lots of work to be done here. But in the same spirit now, I want to describe another numerical experiment, which of course also starts with a spherical cow. In this case, it was sort of a chord isothermal sphere that we put in a 2-parsec box, and we had just slightly over 1,000 solar masses or so in this thing, 1,200, and in the cloud 1,600 sort of in total. And you see the simple profile here. We assumed a speed of sound. There's some scaling you could do here, but the range of experiments we wanted to do was sort of very simple. We said, okay, this is a cloud. Let's imagine all we have is gravity. We let the cloud collapse. Then we said, okay, now let's also assume the cloud is supersonically turbulent, just like we measure from the observations directly of molecular clouds. So it's highly Jeans unstable. At the other hand, the turbulent velocities that we have are as big as the virial velocity of the thing. So the cloud's not going to fly apart, but the initial turbulence value would sort of keep it roughly in that area where it's confined in. Then we said, okay, now, well, we've already observed the magnetic field strength in molecular cloud. Let's also put that one in. Don't invent a lot of parameters. Let's just use a uniform field, and we'll pick a value that sort of gives a reasonable mean flux to mass ratio throughout the cloud. And then on top of it, okay, we'll keep going for a little bit. Then we also went ahead and said, okay, if we have a turbulent cloud that's now going to be fragmenting, we also implemented a sinc particle description, which you heard lots about already. The key thing for us is we really played with the sinc particle description for a long time until it gave a sensible IMF. And so in our experience, it was just a few months. I played with lots of different sinc particle prescriptions. I could get very different answers just based on what rules I invent. And so, in some sense, sinc particles, it's not an equation, it's just an algorithmic toy. So what I really wanted to do is make sure I get a correct IMF. So I get a decent salpeter-like IMF. And then I said, okay, this is great, because now I sort of buy that at least I make sinc particles in sensible locations. They perhaps have decent accretion rates, at least sort of by mass, so that they give the correct IMF that's observed. But then now I can use them as sources for momentum. So here we just use a very simple scaling. I'll say a few more words about that in a second, of observed outflow rates, momentum deposition rates from young stellar objects. So what you notice is we've used magnetic field strengths that are taken essentially from observations. The outflow rates, the momentum injection is taken from observations. And so those are sort of the free parameters in the way I had there. And the rest are very, all the other choices, a spherical cloud, a uniform field, are sort of just idealizations. Yeah?
I guess I'm more confused. So under what criterion do you create sinc particles then? Something other than density?
Oh, it's still actually, it still looks a very regular story. It's sort of high density. We create them at rather small masses, sort of Earth mass things. Then we have a merging algorithm that sort of lumps them together based on a friends of friends thing. Then they have a Bondi accretion rate. I think many things are not that different. Unfortunately, it didn't pay so much attention to many of the others, so I can't tell you exactly whose it's equal to or similar. It's not too crazy. But all I was sort of trying to imply with this is that if I keep changing those things, I kept seeing differences, and I saw exactly in sort of which zones do you pick, how do you remove the gas, do you just suck it off the grid completely, do you do it over time, do you sort of limit the time step of how much gas gets accreted in one, all those. So there's so much freedom there that the key was just, so let me just show you briefly so you believe me, that you get some sort of sensible looking sinc particle mass function sort of a thing, and we don't make much big deal other than sort of rough indications what the different models would give. But the key thing here is it needed to be the right sort of shape, because we use them, right, as sources for the momentum. And so I can't afford to have a sinc particle distribution that's totally off from the IMF, because then I don't believe it would apply to the real world. And so, but I don't see that as a prediction in some sense. Could argue about that. And then we added one more model where I said, okay, we do the sinc particles and the outflows, but we leave out the magnetic field. Right? And so it's, we're trying to understand, get a grasp between the interplay between those two. We use ENSO 2048 dynamic range. We have a periodic box, but when jets leave the box edge, the kinetic energy gets in fact removed. So it's not a periodic box in the sense that the energy would always keep going up as you inject momentum. It really gets damped at the edge of the box, which was one of the big criticisms that the previous work, I guess, by Lee and Nakamura had to face. Yeah, and we could sort of overcome here. Okay, and so I already said all this about the sinc particle mass function. Well, you know, you might get all excited about that. The MHD plus WIN sort of has a characteristic mass scale that's a bit smaller, or a factor of 2 smaller or so than the pure MHD model that's in red. Yeah, it's nice. It's perhaps sort of a sensible mass, but I'm sure we could play with that as well. However, and so then we just looked at observational papers describing the momentum input into these outflows, and we tried to make it as conservative as we could. So what we did is we made the jets as thin as we possibly could. Okay, because if I have sort of spherical explosions, I could argue, well, okay, that momentum couples to the cloud very nicely. But if I make the jets super, super thin, it's not clear whether they could have any impact on the evolution of the molecular cloud, because a thin jet may in fact just shoot right out of the cloud. And just, I keep thinking of a water hose that I'm pointing out of the window, and it's just, you know, that's it. It's gone. It's not going to get wet inside. And it's sort of similarly here, and it's in fact exactly what we then observe. So here's a quick, just the animation of this. I visualize actually the kinetic energy in yellow, and that's how that picks out totally the jets. In density, you wouldn't see it because it's fast-moving material. So just by the continuity equation, you don't have much mass there. But here, doing the kinetic energy, you see it very nicely. Going from black to blue to white, this is the gas density. And the little white dots, I guess, are the stars. And you see you have sort of subfragmentation. So this thing doesn't have a very central region. We've got a subcluster here where actually more massive stars tend to form in the center of it. You can also tell that from the stronger jets that you get from them. But you start getting fragmentation along filaments, very typical, as I'm sure you've seen a lot this week. The many properties of that cloud are actually, I think, quite sensible. And sort of, to me, what really brought home sort of the key, simple thing was really this diagram, where we look at the total stellar mass as a function of time in these different models. And what you see in the hydro model is that after one dynamical time, you have an exponential collapse. Okay, it's not totally exponential. You see this little bend. That's because we use the chord isothermal distribution, right? So there's different mean densities at different radii, and so it sort of slows down a little bit at the very end. You don't really care because you already almost turned half the cloud mass into stars. So this is not a very sensible thing. Well, it's just a sphere collapsing. Now, if we add turbulence, it's just what you expect. It takes one dynamical time for the turbulence to die out, and then you still get exponential collapse. Okay, also not a great model for a stellar cluster. You have to sort of stop the secretion. And I think many models I had seen previously, in fact, were exactly this model, but they just stopped the simulation here or here, where the star formation efficiency still looked reasonable. But if they would have evolved it just 10 million years more or 30 million years more, the model already would actually be totally inconsistent with observations. So this is really just not a good way. You can't assume that I'm going to have a massive star that's going to turn on at exactly this time and then blast the cloud apart in such a fast time scale to sort of save my star formation efficiency in the model. And that's why we were just thrilled when we then looked at this model that did MHD plus WINs, and the character of the curve actually changed. And what you see is it just became a linear relation. So in time, we had a constant star formation efficiency after sort of perhaps an accelerated growth initially on. But then the cloud got itself into an equilibrium. Now, we just looked at the movie, and that was actually surprising, because you look at the movie, you don't get that sense that there is something round or that gets itself in an equilibrium. And in fact, but what it manages to do is every time you would get a little denser, the accretion rates on average on the protostars go up. They inject a little bit more momentum. That momentum couples to the magnetic fields and through Alfvén waves gets transported throughout the cloud and actually slows the further contraction of the cloud. So as a consequence, when you look in the movie, you know, sort of the general scale of where the material is at actually didn't change very much. It's just you built some subclusters. And what we ended up, you can read off the dynamical time right here. You know, we ended up getting up to 6 dynamical times off this clump, and all it's doing is just making stars linearly in time. We were totally thrilled about this, because in fact, at this time is when we made our first 30 solar mass zinc particle. So now my massive stars do not have to be on time. If they're a little early, a little late, I still get sensible star formation efficiencies, and I can allow for all the variations that will happen in these different clouds. And it's that process between the outflows and the B field that just very naturally regulates that star formation you know, has this observed low efficiency. And so, you know, we really thought that's just great. Now, when we remove the MHD and just do the winds, exactly what I was talking about with the water hose happens, and the jets just shoot out of the cloud, and you get almost no effect. Sort of a little bit of a delay. It's sort of a little bit like MHD. So you would want to compare it with this model. It's the winds shifted it from this to over here, but it still continued to just rise. So it's really the combination of magnetic fields and outflows that sort of help regulate star formation on that small scale. And so yeah, you know, there's a lot more one can do here, and I think but the most basic aspects here is we used observed field strengths, observed sizes, reasonable surface densities, reasonable outflow rates, and you already even in this very conservative way of thinking of jets of being super thin, you already get this dramatic qualitative change of how star formation happens. Now, then it's often been argued the velocity power spectrum is sort of a great way of telling the difference. I really would disagree. Actually, all the models we do always get the same velocity power spectrum. The only noticeable difference is that here on sort of half a parsec scale, you see a little bit of flattening on the large scales, and that's purely because the model with MHD plus winds runs for many dynamical timescales. And so we have a small box. We don't have any energy cascading into the box at that point. And so yeah, in this IUS model, we see on large scales a little drop. In reality, of course, you're not isolated. It's easy that you'd always fill up the larger scales here. But sort of on small scales, you don't see kinks or any differences in of the injection scales, which would be way down here. And okay, oh, I guess I had some nice lines. Anyhow, so the neat bit then is that you know, we can do these calculations. Once you have those massive stars, we include the radiation transport and actually follow how the H2 regions break out, and can now modify it. The cloud structure. And as we sort of rotate around, I always find this instructive of whether, if I observationally see this H2 region versus, say, this H2 region, what would I infer? Would I infer the same star formation rate, the same star formation efficiency? Probably significant differences there. And I'm sure you've already seen nice examples of also seeing how dynamic this actually is. How some H2 regions break out for a short time in one direction, then they get shielded by clumps that come right in front of it. Sort of a very dynamic radiation field that you actually have in these clouds. Okay, so why did I do was I interested in present-day star formation at all? For me, it really came from trying to understand galaxy formations, of starting at very high redshift, how the very first stars form, and how the very first galaxies build up. And so we studied a lot of how population 3 star formation worked, and we also developed subgroup models, then how we can incorporate our numerical findings into models that model, say, dwarf galaxies, 10 to the 9 solar masses at high redshift. But what I was always very dissatisfied with was these models of how we include normal star formation in these models, where we just sort of create, you know, stellar particles, 10 to the 3 solar masses, and they have supernova rates and go up. So this excursion to present-day star formation for me was really just building a subgroup model that we then, that has few enough parameters that we can then apply to sort of forest galaxy formation, sort of, you know, dwarf galaxies at high redshift. And we're still not fully there yet, so I just want to flash a couple of results from simulations that do not incorporate this model that I showed that sort of had a resolution element of 100 AU, but give you a sense of in what type of environment it would be embedded in. So this is a simulation. You see the scale here, about 500 parsecs across. This is 2 times 10 to the 8 solar masses total in dark matter. And the simulation included primordial gas chemistry, the physics of population 3 stars. So we make massive stars, follow the radiation transport actually of their H2 regions out sort of the whole lifetime of the star. At the end of the star, we've ran 42 different models of this. Actually, we make different assumptions about the population 3 star mass, whether they die as regular supernovae, as parent stability supernovae, whether they leave black holes behind, whether the accreting black hole actually emits X-rays, for which point then we have a particle that goes at the location where the star was and provides a source of X-ray feedback. And this is actually in particular that example that I'm showing here. But then it includes the metal enrichment, so we follow actually how the metals get transported from these stars. All for the population 3 stars, separately for what we then call population 2, which is sort of a zinc particle description actually, or sort of more regular Jen and Ostraker style star formation recipe using 1,000 solar mass star particles. And again, with metal enrichment, we'll do also the radiation transport actually from these stellar populations. And so, you know, it's a fairly involved thing, sort of the secondary ionizations and X-ray photons and the supernovae from 2 different populations. And the only thing I'm so thrilled about this one, though, is that you have a few 100 million resolution elements over this scale. And it was for the first time I did a galaxy where I really had the sense that it started looking like an ISM. So we have shells, we have elephant trunks, you've got sort of really thinly swept up regions. Normally, and I've done a lot of work on galaxy formation, is we have so few resolution elements that the numerical viscosity just makes things in just very long filaments that might reach down to a disk. The disk itself actually doesn't have much of an ISM at all. But in these very small galaxies, we can actually afford and get down to the stellar scales where it's sub-parsec scales, in fact, where we include the H2 region physics and the supernovae physics. And so if you look at more other physical quantities here, we've got the electron fraction down here, a molecular hydrogen fraction here, density and temperature. The temperature on this side is very high because currently all of the UV photons from the massive stars are happening to escape in that direction. It almost has no escaping radiation towards the right at that moment. In the H2 fraction, you beautifully sort of pick up all these shells that get driven by the individual supernovae and H2 regions of the stars in the galaxy. And this is all done sort of using adaptive ray tracing, so there is no approximations in how the UV gets transported, and you get these perfect shadows that are sort of a key aspect in getting elephant trunks in the simulations correctly. And so the way forward, I think, the things I'm really sort of excited about is combining the previous result I showed, where we did sort of 2 parsec scale, 100 AU resolution zinc particles, and compare this with this full cosmological simulation that actually starts in a megaparsec box and makes many galaxies literally starting at redshift 200, so where you start without any structure at all. There's the combination of these, I think, where we'll get to the next few years. It's just wonderful that the timing's actually going to work out great. With JWST being online, we'll have 100 parsec resolution in these objects. Be amazing. With ALMA, we'll have fantastic resolution there. With the very large telescopes, ELT, the TMT and GMT, will also go not quite, of course, that high redshift, but it'll give us a lot of details and sort of a goal for us to evolve the simulations forward to. And so, anyhow, so that's sort of the motivation coming at this, and of course, there's many other good reasons to study star formation. It's just sort of one particular story. So I just want to impress on you, at least to me, I don't know, like it's hard for me not to see how outflows wouldn't be a really large, play a large role in star formation, because the assumptions that we put into these simple numerical experiments all calibrated by observations, and I don't really see sort of the logic, how the logic here could be wrong. So if that is in fact, that conclusion is in fact correct, it actually gives a very nice way of understanding why the outcome in terms of star formation efficiency can be so similar among so many different clouds, just through this reason that because of your linear star formation rate, you give the massive stars time to form and get rid of the gas in a sensible time scale, and they don't have to do it while during an exponentially contracting background in the back. So there's a lot of issues always in this field of how we talk about molecular cloud lifetimes, and Chris and I had many wonderful evenings doing this, thinking about ideas of how you even define that, what do you mean when something lives 10 dynamical timescales. In this case, of course, when you sort of go back, perhaps just for the, just go back to the initial movie on this, is you have so many dynamical states that you see the cloud in. Sort of at the initial formation, you would just have a very low star formation efficiency cloud here. Still lots of molecular cloud or molecular gas at the point, few stars. But then over many dynamical timescales, it just looked like your regular thing. It's got a whole bunch of stars here, a bunch of stars here, it's got a few outflows there. The thing, it doesn't vary that much anymore. So even if you see it in a time difference of a factor of 3 dynamical times, the change in the ratio of stars that you have compared to the gas wasn't that big. So anyhow, so I think it offers sort of a nice picture in understanding this and sort of ways of how to think about what do you call molecular cloud or sort of star formation efficiencies of molecular cloud. And so what I really hope to see is sort of doing, that we'll end up seeing a lot more models like this that start in making molecular clouds, have massive stars destroy them, argue about all these things that we do, whether, how the winds versus the radiation have an impact, but then really carry this forward and do it for a whole number of generations in order to build up more sensible models where the initial conditions don't look so idealized. So if I have really boxes of ISM that do this at this level of 100 AU scale, follow the formation of stars and the destruction of the molecular clouds, I think those type of calculations will allow us to get a lot of intuition about how star formation sort of over cosmic time works. Okay, so that's all I had on this. I don't know how many of you tried the ENSO tutorial, but perhaps if you have a few questions, we can do that and then spend some time, if you have questions, talk about the code. All right, thanks.
I have a question. So
sure.
Could you do a more careful analysis for the galaxy magnetic fields in trying to distinguish whether your large-scale magnetic field and more turbulent magnetic field? Did you do this, or did you find some large-scale
oh yeah.
structures?
Yeah, you totally do. I mean, actually, you see it very easily visually, I thought, already.
The galaxy looks very turbulent. this point now.
Yeah, so what happens here is, of course, the feedback model that you use is just this polytropic equation of state. So you've always, for all times you have a gas-rich disk. Actually, sort of this one. And so for all times you have a very gas-rich disk. So all these gas dynamics sort of play an even larger role. Like if you imagine a disk galaxy like the Milky Way, at some point, you just have 10% in the gas, and you're much more dominated by the stellar distribution. That will help you to make it a lot more regular, because now the mass in clumps doesn't have such a large effect. But I thought that even here, actually, if you look at the field distribution, just in a slice through the midplane, you already see lots of ordered field. And it's just not surprising. You really amplify on very small scales, and then you need one eddy turnover timescale to actually transport this and get contributions on larger K modes. Again, it's some of these findings are just so simple. I think I don't really see what could be wrong here in that, and I believe that it's really, really, really easy to build up magnetic fields super early on. Very high redshift galaxies will in fact be totally dominated magnetically, and so I'm just sort of thrilled we're finally at this time where we have codes that can actually do this. So we should, I hope that many of you just really start using the field to think about the cosmic rays that will also play a large role. Because it really modifies how the fluid itself behaves. Man, you're totally fresh. It doesn't seem like you've done this for 2 weeks.
Any other questions? All right, well, if not, we will break for lunch a little on the early side.
Okay, great.
Thanks again, Tom.
Thanks.